We've talked a lot about the velocity field. Let's move on now and talk about the acceleration field. Why? Well, force is mass times acceleration, or more generally, it's the derivative of momentum. It's d by dt of momentum, mv. So acceleration is obviously important because if we're going to talk about the forces of fluids on bodies or bodies on fluids, we need to care about the acceleration of those fluids. So how do we calculate or relate the acceleration to the velocity field? So to start with, are these fluids accelerating? Let's take a look at this video on the left. We've seen this flow. This is just with slightly different seating in it. And again, you can tell as it's starting up, or as those parcels are moving through it, that there is acceleration of each one of those parcels. But now look at it in an Eulerian sense. Unfocus your gaze, look at the entire thing at once, and you can see that nothing is changing in the big picture. I could loop that indefinitely and it would never look like it had changed. You could play it backwards, you could play it forwards, you could take one shot and then a later shot and it would look exactly the same. So the fluid parcels are accelerating, but the flow is steady. Likewise, think of that second case, water coming out of a tap. Go do it in your bathroom or in your kitchen. Turn on the tap, especially at a nice slow rate so you can see a nice clear tap jet coming out. It's not moving, it's not oscillating, it's not wiggling, it's not changing in time in any way, shape, or form, but you know that the water as it falls is being accelerated by gravity. So are these flows steady? Yes. Are these flows accelerating? Yes. How do we deal with that? Well, to start with, think back to Phys 115 and ME 212. Think about kinematics. Pause the video for a second here and write out W as a function of t and Z as a function of t. And then if you're feeling like algebra, go through the process of combining those to eliminate t from the equations and write out the equation for W. This is for the tap jet specifically, so think of a chunk of anything, in this case fluid, falling in a uniform gravitational field downward. Pause the video. I'll give you 3, 2, 1. Okay, now let's take a look. The equation for W is there. The position of a falling body is its initial, or sorry, not the position, the velocity of a falling body is its initial velocity plus acceleration times time. And so that velocity should actually be a negative there because g is in the negative direction. So that velocity is negative, not positive. So it's W minus gt. And likewise, you can write out the equation for position. And the position with respect to time is initial position plus initial velocity times t plus 1/2 gt. And again, since we're saying that g is 9.8 meters downward and positive is upward, again, have to fix that. Sorry. If you combine those two, though, you end up with an equation for velocity which does not depend upon t. We know the fluid is accelerating, but there's an equation that tells us the velocity of every point of fluid in that tap jet. And it shows that it's changing, that it is accelerating, but it's not, there's no function of t in there. How do we do this more generally? Well, there's two ways, and let's look at them. The first way we can look at it is by the definition of a differential. Thinking back to Math 116, acceleration is the limit as delta t approaches 0 of the change in velocity, w at t plus delta t minus w at t, over the change in time, delta t. So it's the limit as that delta t shrinks and shrinks and shrinks. That's the definition of velocity. That's the definition of how you take a differential to anything. It's the definition of acceleration and definition of how you take the differential of anything. So let's expand that. What is w at t plus delta t and what is w at t? Well, At some future time, the fluid parcel has moved to a future position. And so W at t plus delta t is W at z plus delta z and t plus delta t. Delta z is velocity times acceleration. That's the change in position. So it's z plus w delta t and t plus delta t. The second term stays the same. It's our reference term. It's still just w at zt. I'm skipping saying not every time because it just takes too much time. And the denominator stays the same. We're taking the limit as delta t drops to 0. It's just staying there as delta t. We don't need to expand that. What we do need to expand now, though, is what is the velocity at z plus delta z and t plus delta t? So I will write in here that this is delta z, just so that we have it in writing. So what is the velocity at z plus a small delta z and at t plus a small delta t? Well, here's where we can use our calculus trick of expanding about a small delta t and a small delta z and ignoring the higher order terms. A function at a reference value plus a small delta is the function at that reference value plus the differential, etc., etc. Let's write that. The velocity at a reference plus a small differential is the function at that reference plus the partial with respect to t times delta t plus the partial with respect to z times delta z. And again, that omega delta t is a delta z. And then we still need the reference value that we had up here. There's our minus w at the reference value. There's our minus w at the reference value. But what we can now do is we've got the reference value there twice. We've got it in the positive and it in the negative, so that cancels out. We've also got a delta t everywhere, so we can cancel out delta t on the top and delta t on the bottom. And so what we're left with is acceleration by the basic definition of any differential is dw by dt plus dw by dz times w. So it's the change in velocity with respect to time plus the change in velocity with respect to position times the change in position with respect to time. So that's your basic definition of any differential. When a function depends upon more than one variable, if you're expanding about a small delta, you need to consider each one of those, need to consider motion in each one of those dimensions. In this case, one dimension is space, one dimension is time. Acceleration as a field can change with position, space, or with time, t. Let's look at the other way that we can get this acceleration field. You're taking ME303 right now. You took 203 already. So you've got some ODEs and PDEs. You will see this a lot in your PDEs course this term, but we can just jump to that acceleration field directly by considering partial and total derivatives. So acceleration in this case is just acceleration in the z direction, which is, by definition, d by dt, not die by dt, but d by dt of w. But w is a function of z and t. So let's do the total differential, or a total derivative of a multivariate function. It is die w die t times dt dt plus die w die z times dz dt. So this is the standard way of taking a total derivative of a multivariate function. We have the change with respect to t times the change of t with respect to t, and that obviously just drops off to be 1, plus the change with respect to z times the change in z with respect to t. But we know that dz dt is by definition w. So in one fell swoop here, we can jump and get the acceleration field is just dw dt plus dw dz times w, just like before. We can generalize from the 1D one component flow that we were considering for that tap to full 3D and 3 component. And we do the exact same thing. We take the entire 3 component velocity field. V here is V equals ui plus vj plus wk. So there's the full 3 components. And all of them could change in x, y, or z. And so we do the exact same thing. We consider the change in v with respect to time, the change in v with respect to x, y, and z. And for the 3 x, y, and z, we multiply by the change in x position with respect to time, u, change in y position with respect to time, v, change with z position with respect to time, w. So the exact same process that we did for the 1D one component case, just expanded out. This is an acceleration field with 3 components, with an x, a y, and a z component. They all have the same form of change with respect to time plus change with respect to position times change of position with time. The thing that changes between all of them is that we have u being the thing that is having the differentials taken for the x acceleration. We have v being the thing that is having its differentials taken for the y acceleration. And we have w being the thing that has its differentials taken for the z acceleration. Everything else is the same. In all of these cases, it's always the change with respect to time plus the change with respect to position times the change in position with time. So di by dx times u, di by dx times u, di by dx times u, same for v and di by dy, same for w and di by dz. This is the general 3-component, 3-dimensional acceleration field. And we give some terms to the 2 types of the 2 parts of this equation, the 2 types of terms, of mathematical terms that we have. So we call this the local acceleration because it's the acceleration that is happening locally at a fixed position. How is the velocity changing with respect to time? And whereas these 3 are called convective acceleration because they are the acceleration that comes from a change in position. Convection is motion of fluid. It should actually technically be called advective acceleration, whatever. Convection relates to movement of fluid. So convective acceleration is the change in velocity due to change in position, due to movement in space. So local acceleration and convective acceleration, both of those cause an acceleration. When we were talking about the tap, we expressed that as an acceleration field that had solely a convective acceleration term. There was just the w di z term in there. But you can see there's 12 different terms here, 3 di by dt's and 9 di by change in position with respect to, change in velocity with respect to position terms. Any one of those 12 terms causes an acceleration. So we call this full thing the material or substantive derivative. We give it the term or the symbol capital D by dt. That's just a shorthand because it gets really long to write out those 4 terms. But capital D by dt means di by dt plus u di u di x plus v di u by di y plus w di by di z. You can, of course, express this in, I don't know, radial coordinates or cylindrical or spherical coordinates. We will express it in streamline coordinates, but not until later in this course. It's always just a change with respect to time plus a change with respect to position times the change of position with respect to time. It's always the same thing for the material or substantive derivative. And that material derivative relates the Eulerian and the Lagrangian perspectives. So the acceleration of any fluid parcel is, from the Lagrangian standpoint, the change in the parcel's velocity with respect to time. And from the Eulerian perspective, when we are unfocusing our gaze and looking at the entire velocity field and the entire acceleration field, the Eulerian perspective is the material or substantive derivative capital D by dt of velocity. Those two things are interrelated. We can consider a single parcel moving through a velocity field. We can consider an entire velocity field. This is how those two things are related. We're going to use both Lagrangian and Eulerian perspective in section 2 to relate the acceleration of fluids to the forces on them and vice versa. And those forces are pressure forces, shear forces, etc. But before we get to that, we need a little bit more of the basic maths of the flow field before we're going to be able to fully understand the calculus of conservation of momentum on a fluid element. So there's three more things that